All right. Excuse me. So the thing that's really important here is whether you're starting with the derivative graph or the original function graph, because the rules are very, very different. So where the derivative is 0 is important. It's kind of that's what you're looking at. So when the derivative is above the x-axis, that means that it's increasing. This is just background stuff that you probably know. And then below the x-axis, it's decreasing the original function.
Yeah.
Okay. So a local maximum occurs when you go from increasing to decreasing. So basically, wherever it crosses, wherever the derivative crosses the x-axis, one way or the other. So because it's above here, then below.
Yeah.
The answer to part A, which up to down here, is x equals 4. Because it's positive and then it's negative. Similarly, B is where the derivative. I mean, maybe I should do this in terms of derivative. It's plus to minus. So the minimum is going to be minus to plus, because that corresponds to like a decreasing original function, decreasing, and it's increasing again. And that's x equals 6, where it crosses that way.
Yeah.
Okay. So part C kind of already answered that here, where it's increasing. That's where it's above the x-axis. So it's above the x-axis from 1.5 to 4. And it has to be an open interval, I guess. And then again from 6 to 7. So it's parentheses, not bracket.
Okay.
Decreasing, it's decreasing where it's below. Okay, because you're obviously going to get something different on your test than this, but this is important. So it's decreasing from 4 to 6.
Okay.
All right.
And the fact that the graph is for the derivative of f of x, and then it asks about the value of just f of x, not the derivative of f of x. Does that change anything?
Yeah, all this stuff is about the original function.
Okay.
But like you could sometimes, I mean, they almost always give you this one, but they could give you a graph of the second derivative if they're really being difficult.
Yeah.
But that doesn't yeah, I mean, that's standard here. Okay, so part E, okay, I made a line there because these are now kind of like all second derivative things.
Yeah.
So it's like if you were given f of x, it's like what you'd be looking for with f prime of x. But because you're given f prime of x, that they apply to f double prime of x. There's some overlap here. So we can talk about where it's concave up and concave down. First, I think those are easier. Where it's concave up is where the f prime is increasing.
Okay.
Meaning it's going up and to the right. Okay. So like it's increasing from 1 to 2. So now we're doing this out of order, but I'm sorry, from 1.5 to 2.
Mm-hmm.
Okay. And then here at 5, there's a min, and it's increasing from 5 to 7.
Yeah. Okay.
Okay. And then decreasing is where the derivative is I'm sorry, it's concave down where the derivative is decreasing. Mm-hmm. So it's where it's going down and to the right. So that occurs from 2 to 5 because it's going down and to the right. Yeah. So the points of inflection, you're looking for a min or a max of f prime. So we're looking there and then here at 5.
Okay.
And it's an inflection point if it goes from increasing to decreasing or decreasing to increasing.
Okay.
So like here, notice like at 2, notice it's going from increasing to decreasing. So that's an inflection point.
Okay.
Down here at 5, it's going from decreasing to increasing. So that is also one.
Okay.
So everything I just did, like there's like, it's like a different thing to remember for each one.
Yeah.
And I know it's a lot to ask to do, but that, it's very easy to get confused, meaning like use the wrong one for something. So
just study it.
Yeah, you just have to learn it somehow.
Memorize it, make sure you know it.
Yeah.
Yeah.
Okay. Okay. Is that okay? Or can we move on to number 2?
That makes sense.
Great, great, great. Okay, the accompanying figure shows the graph of the derivative function of f. The domain of f is the closed interval. Okay. All right. So again, like that's really important that you know that this is the derivative. Sometimes I write it just to make sure like I don't somehow forget that. Okay. So critical values. It doesn't say whether they're of the derivative or the original. Okay, so part A, identify class the x coordinate of each critical value. So there's this point, and this point. X equals -2 is a critical point of f of x.
Okay.
And the reason is because the derivative goes from positive to negative.
Yeah.
And in terms of the original function, that means it went from increasing here, even though this is going down, to decreasing here.
Yeah.
So that's for sure one of them. Justify your answers. You actually have to like do something with what I just said there. Maybe even say like f prime of x positive to negative. I like sign charts. Like I like showing at -2. I guess there's a bracket there, -3. And then one at 0, like saying like, oh, this one from plus to minus. So
yeah.
And let me just do one more thing here that like in terms, I'm using a different color. In terms of the original function, here's what the original function's doing. So there's that max right there, because it's literally going from plus increasing to decreasing with that sign chart. Okay. So similarly, at x equals 0, that's a critical point of f of x. And it's because the derivative goes from negative to positive.
Yeah.
And so I should be labeling these. This is a max of f of x, and this is a min of f of x.
Okay.
Because it's going to come kind of down like a u.
Yeah.
Okay, so now we have to say, well, what is x equals 2? And I'm kind of leading you there because it's not the same as the other 2 points.
Yeah, because it doesn't go from positive to negative or negative to positive.
Exactly, it goes positive to positive.
Yeah.
And the same could be true if it was negative to negative. It's nothing.
Yeah.
So in terms of the original function, what it looks like is like an increasing and then it's still increasing. And it's nothing.
Yeah.
I mean, in terms of this, I mean, maybe this, but okay.
Okay, so the 2 critical points would be x equals -2 and x equals 0.
Yes. Now, what's unclear to me, and is that for the derivative has its own critical points. Like that's an inflection point, and that's an inflection point, and that maybe is something we can talk about that. Okay, but I don't think it's asking for that. But it's very unclear. Like the question should say critical values of f of x.
Yeah.
But I didn't make this question, so I'm saying it's a little ambiguous, which is often the case when these things are just grabbed arbitrarily. So
Yeah.
where is the function in, where's f? See how it's talking about f now is increasing? It's increasing when f prime of x is above the x-axis. This is the only one where you actually care about like x-axis. Most students try to justify something up, but this is the only time. So it's above the x-axis here, then again from 0 to 2, and then again from 2 to 3.
Yeah.
So we would say, and these are open intervals, -3 to -2, comma 0, comma 2, and then comma 2, comma 3.
Yeah.
All right. Now you could maybe justify that at 2, it is still, it's neither increasing nor decreasing. So you might be able to get away with like including it, but it's because it's not doing anything there. It's a horizontal tangent. It's this picture over here. So that's why it's not included. Part C, so concave up, concave down. So part C, it's concave up when f prime of x is increasing, going up and to the right. So if we go back and look at the original function, it's increasing from -1 to 1, and then again from 2 to 3, because it's going up and to the right. So if you like flashcards, I mean, that's the kind of stuff that I would recommend writing those words down, like up and to the right.
Yeah. Okay.
And it's going down when f prime of x is decreasing, because sometimes that still doesn't mean anything. Like, what do you mean decreasing? Well, it's down and to the right. And it's going down to the right from -3 to -1, and then from 1 to 2. And these are always open intervals.
Yeah. Okay.
Do you think you could do one like this on your own on the exam?
Yeah, I just need to review the, like, when it asks for concave up, it's increasing up and to the right.
Yes.
Review like those the rules.
Yes.
Yeah. And
Okay.
the general basis.
So you can actually do the same set of 7 here for letters for 2. It does just a couple less. Like you could do the same analysis for both of them if you wanted like this practice later on.
Practice.
Okay. So like 3 is a good question because it's like an analytical question without a graph. If you want to do that, you got to find the same thing, increase and decrease, up and down. It's kind of long though, so
no, it's fine.
Fine. Okay.
Whatever you think is a good question.
Yeah, I would think it's a good one to look at.
To know for the test.
Yeah. Based on your past experience, are the tests about the same as the review? Are they more difficult, easier?
It just gives us a lot of review, which is sometimes difficult. Like she just gives us the textbook review. And sometimes I wish you would just give us like a paper with like 10 problems on them, similar ones that would be on the test.
Yes.
Because she gives us just so many questions and then you kind of, she like just merges them kind of on the test, which makes it confusing. But normally the tests are pretty hard. So, I mean, but we're allowed to retake.
Okay. Well, this question here, question 3, it's got a bunch of parts to it. Basically, you have to be able to be really strong at finding your first derivative here and then your second derivative. So your first derivative is product rule. Okay, so your product rule here is x squared e to the 1 over x squared times -2 over x cubed plus 2x e to the 1 over x squared. Okay, so you can look at that later if you want, but you only simplify if you're going to reuse the derivative, and we are, because we're going to actually take a second derivative here.
Yeah. Is the -2 over x cubed, where does that come from?
That comes from chain rule of this, because that's really x to the -2 power. So
Yeah.
the -2 comes out in front, -3 power goes down
Okay.
in the bottom there. So you get some cancellations here. So y prime is -2 e to the 1 over x squared over x plus 2x e to the 1 over x squared. Now we are going to take a second derivative. We're not going to do it right now. We're going to set it equal to 0. So when you set something equal to 0, this is where it's like a heavy dose of pre-calculus college algebra stuff. So you have to factor out anything that's common to both. So like e to the 1 over x squared is common, and you can actually factor out a -2 from both. So you get 1 over x here minus x here inside parentheses.
Okay.
Okay, so this is very important. Well, most things are, but e is never 0. E to anything, I don't know, e to something, f, whatever, or well, e to 1 over x squared does not equal 0 ever, but e to anything generally never equals 0. So that's why you factored out. So you really just have to set this 1 over x minus x equal to 0. And you end up solving this x equals plus or minus 1.
Okay.
Okay. So those are your two critical points. You make a sign chart here. -1, +1, and then you have to test values. Hopefully this is something you've seen in class.
Yeah.
Okay. So like I'm going to suggest we test 0. And I draw them down here so they're away from the actual sign, the actual numbers that you care about.
Yeah.
One of the things that students really don't understand is that you actually don't care what the number is, you care whether it's positive or negative in here. Okay. So like on the outside here, this is always negative. Okay, it's always negative. So we don't have to plug it in there. You can, but you don't need to. Okay, so let's just do this 2 first. 1/2 minus 2. Well, that's negative because -2 is bigger than 1/2. So you have a negative times a negative. That makes this positive. Now I messed up here, believe it or not. 0 is actually not allowed. 0 is a place where you're dividing by 0. So we actually can't test 0. It's a place where the derivative is undefined. So we need to test something else like 1/2. Okay, so 1/2, 1 over 1/2 is 2, 2 minus 1/2, that's a positive. Positive times a negative is negative. And we do the same thing, we can test -1/2. This is -2 plus 1/2, so that's a negative times a negative, that gives you a positive. And then, did I get these right? Yeah, x squared equals 1. Okay, so -2, this is positive, this is negative, so you get a negative. Okay. So you can say, oh, it's increasing from -1 to 0, comma 1 to infinity. And then it's decreasing from -infinity to -1, comma 0, comma 1.
Yeah.
Okay. But this thing that I missed here, this is really important here. You not only look where the domain is restricted, but also where the derivative domain is restricted. So you can't divide by 0. But this place at 0 is not, it's nothing on the original function, because you go back to the original function. Well, actually, the original function cannot be defined at 0, so I take that back. But places where the derivative is not defined, like they're neither min nor maxes. Like you can't, there's not a min or a max here, even though it changes from plus to minus because the function's not defined there.
Okay.
So I apologize if that was unclear, but only this point and this point are eligible for like, min or max.
Okay.
So over here, it goes from decreasing to increasing. So this is a min. And this one here also goes from decreasing to increasing, goes to a min.
Okay.
But this is nothing in the middle here. You can always graph these like with Desmos or something similar, just as like confirming what you already know.
Yeah.
Okay. So the next set of stuff asks about the second derivative. And that's why you simplify your first derivative. Now you might ask, well, why wouldn't I use this? You could. I don't like using the factored form for derivatives. It's, the more math you take, you get to have a little bit more like preference in how you do stuff. So the second derivative here, it's kind of horrible, but we can keep going here. It's minus 2 over x. And then the derivative of this, like if you're ever unsure, just go back to your previous line and be like, what did I do there? It was e to the 1 over x squared times minus 2 over x cubed plus e to the 1 over x squared. And then the derivative of minus 2 over x becomes 2 over x squared. Okay, and these two terms come from this one. And then the derivative of this we got to do next. Okay, see how messy this gets pretty quickly. 2x e to the 1 over x squared, okay, times minus 2 over x cubed plus 2e to the 1 over x squared. So these all have an e to the 1 over x squared in them. And they actually all have a 2 as well. Boy, this is really bad. This is yeah, it's not ideal. So I think you can actually factor out this yeah, so let me simplify, I guess, first here. So there's e to the 1 over x squared in all of them. And then this first one becomes 4 over x to the 4th plus 2 over x squared plus 2x plus 2. Oh, this one is, I'm sorry, I missed this one. This one is negative 4 over x squared. Okay, plus 2. Like that.
Okay.
So these two actually combine. These make minus 2 over x squared. Negative 2 over x squared. And this is going to be a little bit weird, but you can actually factor out a 2 out of all of them and over x to the 4th from each of these.
Yeah.
So it ends up being 2 plus negative x squared plus x to the 4th.
Okay.
And then, so this is really x to the 4th minus x squared plus 2, and then does this factor? It does. Factors to that, and then this one you set equal to 0, so you get x squared minus 2 equals 0, x equals plus or minus square root of 2. I would not expect you as a calculus student to be able to do this, but it is like it is like totally doable. It's very long.
Okay.
So then you do the same thing with your.
Give one this long.
Yeah, they usually give you a polynomial so that you can factor it quickly.
Yeah.
And by an x squared plus 1 is never 0. That's why we don't include it. So you do the same thing here. This is your second derivative sign chart. So you just test points. 0 is also not included, so you can't test that. So you can test like 1 and -1, thankfully, and then like 2 and -2. And you're testing them in this factored derivative. So this first part is always positive, thankfully. This one is always positive. So it really comes down to whatever the one on the inside there is.
Okay.
So that's kind of helpful. So when you put 2 in, you get a positive 1. 1 minus 2 is a negative. This is also a negative, and then this is positive.
Okay.
And just looking at sign and not the actual value. So this is an inflection point. This is an inflection point. Okay, and even if this changed from plus to minus or minus to plus, this is not, because it's not part of the domain. If you look from the original function there. Okay, so this helps you to figure out where it's increasing and decreasing. So it's increase. I'm sorry, concave up, concave down. Let me misspeaking here. Concave up from minus infinity to minus 2, comma, which side is square root of 2, square root of 2 to infinity, and it's concave down from minus square root of 2 to 0, 0, comma, square root of 2.
Okay. Got it.
Would 17 would be maybe good to look at next, maybe.
Okay.
Just try that. I hope this is helpful. This seems like so much work that just it's
Yeah. So much busy work.
yeah. Okay. So notice here that they're giving you the derivative, they're not giving you the original function. But you can still do it. You can still do everything we have. It just cuts down on that step of taking the derivative. Okay, so to find local max and local mins, you have to set the derivative equal to 0. You have to set 6 times x plus 1 times x minus 2 squared equal to 0. And because it's already in factored form, you get your two critical points, -1 and +2.
Okay.
So we're going to test 0, 5, I don't know, -5. And again, you only care whether it's positive or negative.
Yeah.
So like 5. 6 is always positive. 5 plus 1 is positive. 5 minus 2 squared is positive. So positive times positive times positive gives you a positive. Now at 0, positive. 0 plus 1 is positive. 0 minus 2 is negative, but you're squaring it, so it's
Positive.
positive. Okay. It's a mistake to think these always alternate. I remember thinking that at some point, but they don't. So then negative, positive, negative. This one's -4. Negative squared is positive, but you have a negative in there, so it's negative. So there's actually only one place of interest right here at -1. The function's going from decreasing to increasing, the original function.
Okay.
So that would be a min. So B, we'll do part B. There's a min at x equals -1.
Okay.
And you're probably thinking, well, what about A? Well, there's no place where it goes from positive to negative, so there's no max.
Okay.
Is that clear?
Yeah.
Okay. To find part C, we have to take the second derivative. We have to do a y double prime here.
Yep.
Yeah, it's get some more. Okay, so this product rule. So I'm gonna choose this to be like my first, and then this to be the second.
Okay.
So it's 6 times x plus 1 times 2 times x minus 2. The derivative of the inside function is 1 plus x minus 2 squared, and then the derivative of this is just 6. Believe it or not, like.
Okay.
So it's not too bad. And yet, like, you want to factor out anything that's common. So if you aren't good at this, like you're going to get this on the exam. So just plan on it. So there's a 6 in both. There's an x minus 2 in both. Okay, so then like what's left over? There's a 2 here and an x plus 1. And on the right, there's an x minus 2.
Okay.
Okay. So on the inside here, you actually do want to distribute and simplify. So it's the 3x plus 0. Okay. Just 3x on the inside there. So you're down to 6 times x minus 2 times 3x. So your critical values are at x equals 2 and x equals 0. You make your sign chart here again. I use a number line.
Yeah.
I think it's easier. So you're testing them in this factored form, simplified form. Okay, so like we can test 3, 1, and -3 maybe. Okay, so 6 is always positive. 3 minus 2 is positive. 3 times 3 is positive. That's positive because positive times positive times positive. At 1, this is negative x minus 2. Positive times a positive gives you a negative. And then over here at minus 3, negative, negative, positive. So that becomes positive.
Got it.
So an inflection point occurs when you go from positive to negative or negative to positive. So this is an inflection point, and this is an inflection point. There's no domain restriction either, so we didn't have to worry about that.
Yeah.
I'm gonna start there.
For like writing it, when she asks for inflection point, should I say x equals 2 comma 0, or how should I write that?
There's one at x equals 0 and one at x equals 2.
Okay, so x equals.
Yes. Now you may want to give her the y value, but if you go back and look here, this one you don't know the original function, so you wouldn't be able to do that.
Yeah.
And if you look at like the original ones, the first ones we looked at, like I said, there's an inflection point at x equals 2 and x equals 5, but since we don't have the original function, like you don't know where they are. It's not on this graph, so you can't. But when they give you,
I don't think the y values are very important for her.
but when they give you, you like here the min and the min, like you can get the y value because you have the original function.
Yeah. Okay. Makes sense.
All right. So we should do 25.
Okay.
As I'm trying to pick one from each group for the moment, and
Okay. Yeah. No problem.
this could be somewhat unclear if you've never seen it before. So why are you doing that? Okay. Okay, the velocity is given here, and they want you to find the position function. So if I give you the position function, if I say s of t equals whatever, v of t, the velocity is equal to the derivative of this function.
Okay.
Okay, like that's a straightforward. And the acceleration of t is the derivative of velocity. And maybe you know that. I don't know how clear that is, but like you probably have seen that in class. The challenge with this problem, this is like in math, there's all these like forwards and backwards problems. This is a backwards problem. They're giving you the derivative. And they want to know what it came from. What is the original? So what do you take the derivative of to get this?
4.9 t squared.
Okay, plus that gives you that one.
5t.
Okay, good. Okay, but there's something missing here, because let's say this was plus.
Oh, this is the c. The
Yes.
plus c. Okay.
Yes. Okay. And by the way, the second half of this course is you do a lot more of this. So you're feeling really good about yourself, but you're not done, because they're actually giving you a point here. And this point is used to find c.
Okay.
They tell you that s is 10 when t is 0.
Okay.
It's kind of like finding a b in slope formula.
Yeah.
Some ways. Okay, so this isn't hard. I mean, you know how to multiply by 0, but you do have to know how to execute these steps. So c is 10, and then you put that back here, then you have to rewrite it. So s of t equals 4.9 t squared plus 5t plus 10.
Okay, that's the answer.
That's it. Yeah. Now, if they give you acceleration, you have to do it twice.
You have to go from acceleration
to velocity.
Velocity.
Yes. If you want, we could do 26.
Yeah.
Okay, let's do it. Okay, so first thing is they're giving you the acceleration. You want to find velocity. So what do you take the derivative of to get 32?
32 some variable.
T.
T.
Yeah, we're using T. You could use X, I guess that'd be okay. But there could have been a constant, right? There could have been 32T plus, 1 billion.
Yeah.
We don't know. Now this is key, is you actually do want to solve for the constant right now. You don't want to wait.
Okay.
So they're telling you the velocity is 20 when T equals 0. So that's a point. That's a point on this 0, 20. Okay, and it is not the case that the constant is always this value. Just don't make that mistake here. So 20 equals 32 times 0 plus C. Okay, it does so happen to work that C is 20. Okay, but it will not always work that way. Put that back in here, and then you rewrite it. Okay, so now you want to find position. And you have to say, well, what do I take the derivative of to get 32T? What do I take the derivative of to get 20?
Huh. Okay.
And this is just the hardest part. It's because it's going backwards. You know how to go forwards, you don't know how to go backwards.
16, is that, yeah, 16T squared plus 20T.
Yes.
And then we would do the plus C, right? Yeah. Okay.
Yes. And then you got this other point here. You got, well, it's 5 when T is 0.
So then we plug that in.
Yes.
Okay.
So 5 equals 16 times 0 squared plus 20 times 0 plus 5. So 5 equals, I'm sorry, plus C. C equals 5. Okay. So you got your final answer. S of T equals 16T squared plus 20T plus 5.
Okay.
Okay, so why don't you navigate for us here? We have limited time, so I don't want to just arbitrarily choose problems. Like,
Yeah, no problem.
anything else jump out at you for us to?
Huh. I'm not sure. Let me look over it.
Okay.
Any problems I didn't get? No. I'm gonna look at what she usually has. What are they called? Like the overviews of each section on the test, because she grades
Okay.
the section. So I'm gonna double check those overviews. The content strands, that's what they're called. Okay, so section A is optimization. Section B is differentials and linearization. And then section C is related rates, and section D is connecting F with F prime and F double prime graphically and algebraically.
So we've done a ton of D.
Okay. Yeah, the first whole thing that we did was that one.
Yes.
Differentials. What is optimization?
There are problems like 47, 48, 49.
Could we do one of those?
Sure.
Whichever one. I don't have a preference.
Okay. Thought I saw another one. I guess not. We'll just do 47 for now, and then find the dimensions of the largest open top storage bin with a square base. Neglect vertical sides to be made from 108 feet squared of sheet steel. So what they're saying is, like, I call this like more like the pizza box problem, but they give you a rectangular sheet, and like you can fabricate that into a box.
Yeah.
And let me go this way, but it's got an open top. So that's open. Okay, but the base is x an x because it's a square
Mhm.
base, and then the height we'll call the height y. Okay, so what we're trying to maximize, because there's I'm sorry, I should have jumped said a few other things here. So there's always sort of a constraint equation,
Okay.
and that's the one that's going to use this 108, and the second is this optimization equation.
Okay.
So the optimization equation here is volume is x squared y, and that's what we're trying to maximize. But the problem here is that it has both an x and a y in it. Okay, so this constraint equation, this other thing that we're going to generate, you're going to use it to solve for usually y.
Yeah.
Okay, so this open box has 5 sides. It's got the bottom, which is x squared, and then it's got 4 sides around. So your bottom here is x squared, and then you have 4 of these xy sides, and that's what you're getting. That's what this 108 makes. Like this 108 is cut into a bottom, front, back, left, and right side.
Mhm.
Is that okay? Clear?
Mhm.
Okay. So notice that like this has x and y in it also, but you're not trying to optimize it. So you solve it for one of the variables, usually y. So this one actually can be reasonably solved for y. It's 4xy equals 108 minus x squared, and then you divide both sides by 4x. So y equals 108 minus x squared over 4x.
Okay.
And I'm not sure if it's good to like reduce yet. We'll bring this equation down here. So the volume is x squared times 108 minus x squared over 4x.
Mhm.
Okay, so one of these x's in the bottom cancels with this one, and then you can multiply it in. So volume is 108x over 4 minus x cubed over 4.
Okay.
And then 108 is divisible by 4, I think 54. Yeah, so it becomes 27x minus 1/4 x cubed. The reason you do all this is because you are going to take the derivative. And the simpler this is, the easier it is to take a derivative. And all of these optimization problems, you always take a derivative and then set it equal to 0. So the derivative here is 27 minus 3/4 x squared. You set it equal to 0 and solve for x. Okay, so this is 27 equals 3/4 x squared. Multiply both sides by 4/3. 36 equals x squared, and x equals 6. Since you probably don't have a calculator on this, tell me if I'm wrong, but the numbers should come out nice.
Okay.
You don't really need to do anything else beyond this because like you only have one critical point. I know it's plus or minus 6, but the side can't be negative. So you just go with it. Like you should use what's called the second derivative test or make a sign chart and prove that it is the min or max, but you only find one. So it's usually good enough.
Yeah.
Sometimes though, you miss what it's actually asking for. So x is 6, that's true, but it wants the dimensions. So that means you need both x and y. So you have to, it's like when you're solving systems, like you weren't done when you found x, you had to go back and find y.
Yeah.
You use this equation here, which is kind of horrible, but it is there, 108 minus 6 squared over 4 times 6. So this ends up being 36. 108 minus 36 is 72. 72 over 24, x is y is 3.
Okay.
So the process is you draw a picture, you set up some sort of constraint equation, usually with the given value, almost always with the given value or values, and then you have an optimization equation. You solve the constraint equation for y, almost always y, sometimes x, but usually y. You plug it back in, take a derivative, set it equal to 0, solve for x. If it sounds like a lot, it is. These are slow.
Yeah. Okay. Mm-mm.
Oh, you said not 53, not 47 either, not 49.
No, 49, I believe, was on there.
Oh, of 47, not
Oh.
47. Sorry, not 47, not 49. We got a little time left here. What problem would you like us to look at next? Oh, you said linearization
Yeah.
or differentials?
Yeah.
We should do one of these 27 through 30s.
Okay.
That will be a good way to close out here. Okay, find the linearization of the function at x equals a. So the linearization of function is a really complicated way of saying finding basically the tangent line.
Yeah. Are we doing 27?
I'm sorry, yes.
Okay.
Okay, so the linearization requires the value, it's f of a plus f prime of a times x minus a. So you need two things. You need f of a, and then you need to take the derivative. Okay, so this is our final form, but we're gonna do these things first. So f of x is tangent of x. F of minus pi over 4 is tangent of minus pi over 4. So go to your unit circle there. Minus pi over 4 is right here. X and y are opposite in sign here, but they're the same value. This also has a slope of -1. So that is your value there.
Okay.
Your derivative, your f prime of x, is secant squared x. And then you have to evaluate it also at the same place. So it's secant squared of minus pi over 4. This is really 1 over cosine squared of minus pi over 4. Cosine is the x value here. The x value is √2 over 2. So it's 1 over √2 over 2 squared, which is 1 over 2 over 4, or 1/2, and that becomes 2.
Yeah.
So that gives you the two things you need, because you need the value. So we're going to use this function here again. Let me write it down here. You need the point of it. So this f of a is what we found to be -1. That was this line right here. And the f prime of a we just found to be 2. And we know that a is minus pi over 4. So you just put those numbers back in. L of x equals -1 plus 2 times x minus pi over 4.
Okay.
So you have to take the derivative, evaluate it. You have to also evaluate the original function. It's very similar to finding a tangent line, which I think you've done. It's almost identical. It looks maybe different, but it's not. So it's you're just not writing it in mx plus b form or y minus y1 form. Although you kind of are, like if you move this point over, it's kind of like y plus 1 equals slope x minus x1. It's actually the same.
Yeah.
So okay, thank you for contacting me for this lesson.
Yes,
If you
thank you.
ever need, yeah, you're welcome. If you ever need one like this outside of what I normally offer, just let me know. Do my best to accommodate you, and I'll send you the PDF of the notes here shortly.
Okay, thank you so much.
You're welcome. Have a great day. Bye now.